All right. So in the last lesson, we introduced this idea of standard electrode potentials, which is an electrode value for a half equation, comparing it with the standard electrode potential, which is 0 volts by definition, which gives us a value we can then combine, and we could say, okay, if I put a silver half cell and a zinc half cell together, what would be the overall cell potential there? Or I could just use it to make a prediction about whether a particular reaction would happen. Now, that might be fairly straightforward for displacement reactions. You might be familiar with the reactivity series. You know that zinc will react with copper 2 plus solution, but you'd know that silver wouldn't react with calcium 2 plus. But you might be less familiar with the E0 values for things like the halogens or other oxidizing agents, or even some ionic half equations where we don't go straight from the metal to the ion. We maybe play around between two different ions. And there are data booklets of these. Here we are, a data booklet with hundreds of values, all for all these different possible half cell reactions. And we can then combine those and make a prediction about whether or not a reaction will happen. So, so if I said, okay, will ion 2 plus react with I2? Will ion 2 plus react with iodine? Okay, so we look at our table of data and we think about, well, what's going to be formed? Well, ion 2 plus could form ion 3 plus, and iodine could form iodide. Remember that we have to have a reduction and an oxidation half equation. All of our electrode reactions are printed as reduction potentials just by convention. So if I want something to be oxidized, I've got to swap it round. The question's about ion 2 plus, so I'm swapping this reaction round. I don't have any ion 3 plus to react with, I've only got ion 2 plus. So I've swapped that one. If I swap the direction of the equation, I swap the sign of the E0 value. So ion 2 to ion 3 would be minus 0.77, and iodine to I minus would be plus 0.54. Stick those together and we have, well, a number. The important thing is it's a negative number. And remember, the rule is if the E0 for the cell is negative, the reaction will not happen. End of. The reaction will not happen. So the answer is no. Ion 2 plus solution and iodine solution would not create any kind of reaction. Okay, so that's handy in itself. Let's just look at the data in a bit more detail. You might notice that the data is usually printed in numerical order. So we start off with the big negative numbers and then go down to 0 and then go up slowly with the positive numbers and reach the high positive numbers. So my first question is, on this table here, where's the strongest oxidizing agent? Where's the strongest oxidizing agent? So by strongest, what do we mean by strong? Well, we talked about the strength of reducing agents and oxidizing agents in the halogens topic, but now we can actually put a number on it. We can say permanganate, when permanganate reduces, and therefore permanganate is acting as an oxidizing agent. When permanganate reduces, it does so to the tune of 1.51 volts. When chlorine reduces, it would do to the tune of 1.36, it's less. So, very simply, permanganate produces more volts. So permanganate is the stronger oxidizing agent. So on that table, down there in the bottom left, is our strongest oxidizing agent. Oxidizing agent. Remember, oxidizing agents are reduced, so they're gaining electrons. Okay, well, let's ask the other question then. If that's the strongest oxidizing agent, where's the strongest reducing agent? Generally, when I ask this question in a live lesson, those students immediately think opposites, you know, because we're all quite good at that. So if permanganate down there is the strongest oxidizing agent, then surely zinc 2 plus must be the strongest reducing agent. No. What zinc 2 plus is the weakest oxidizing agent. Because if I put zinc 2 plus in a solution, it would react to the tune of minus 0.76 volts. And remember, negative numbers are not the downhill, they're uphill. Overall values for E0 for the cell with a negative number is a no-go. That means the reaction won't happen. So if I've got something which is already carrying minus 0.76 of a volt, then it's going to have something with more than that in order to make that reaction happen. So zinc 2 plus, very weak oxidizing agent. But zinc over there, well, of course, if zinc reacts, it goes to form zinc 2 plus. That's going in the opposite direction to the arrow, which means I change the value. So when zinc reacts, it would react to the tune of plus 0.76 of a volt. That makes it the strongest reducing agent. Zinc, solid. Not zinc 2 plus, that will be a weak oxidizing agent. Zinc, metal. In fact, all the metals are pretty good reducing agents, but zinc, on this table of data, right? Obviously, if I put in a more reactive metal, magnesium or calcium, it would be a stronger reducing agent. But on this table of data that we've got in front of us, zinc is the strongest in that list. We could ask more subtle questions. We could say, what's the strongest oxidizing agent on this list, which is a halogen? So again, oxidizing agents are all on the left here. So the oxidizing agents that I've got to choose from that are halogens, chlorine, iodine and bromine. Which of those is the strongest? Well, it's going to be the most positive, going from left to right, because we're looking at oxidizing. These are all oxidizing agents, right? So chlorine to chloride gives us the bigger positive number than bromine or iodine. But then ask yourself, which is the strongest reducing agent that is a halide? Well, now I'm looking over here, and of course I'm going in the other direction. So iodide to iodine minus 0.54, which doesn't sound that flash, but it's still a more positive number than minus 107 and minus 1.36. So the strongest oxidizing agent, which is a halogen, is chlorine. The strongest reducing agent that is a halide is iodide. So we can use this table to make comparisons. We can use it to make predictions about whether or not reactions happen. And we can also write those reactions in a very particular way, which used to be called a cell diagram, but that's a very confusing term, because when you say diagram, I think, well, I'm going to be drawing beakers and wires and salt bridges. It's now called a cell representation. If I have a cell, let's say I have the zinc copper cell. What's happening in that cell? Well, zinc is reacting and forming zinc 2 plus. Zinc solid reacts and forms zinc 2 plus. Then we have the kind of the middle of that cell diagram. So we usually draw a double line. And then the other side of the cell, the copper 2 plus ions are reacting and forming copper solid. In the old days, we would put a sort of less than greater than sign around that like a pair of bookends, but those seem to have gone out of habit. But that becomes our cell representation for that reaction. So what do we have? Well, we have a single vertical line wherever we have a change of state. And we have our double vertical line for the middle of the cell or for the salt bridge. Okay, what if I had magnesium and the hydrogen electrode? So magnesium against the hydrogen cell. Well, magnesium will be oxidized, and that's another rule. We always put the thing being oxidized on the left. So we go from oxidation here to reduction over there. So magnesium's being oxidized, magnesium solid, then there's a state change, magnesium ions, and we have the salt bridge. What do we have on the other side? Well, we have H+ ions forming hydrogen gas. That's fine, but that's not the end of it, because of course hydrogen ions and hydrogen gas don't conduct electricity, so we need an electrode in there. The electrode is made of platinum, and that's another state change, so we'd need another straight line there. So magnesium is being oxidized to magnesium ions, separated by a vertical line. Salt bridge, hydrogen ions are being reduced to H2 gas. Platinum is carrying the electricity, so we have a straight line separating those two. What if I had iron 2 reacting with, let's just go with silver for the moment. Okay, so which direction are we going to go? So iron has to be reacting to make iron 3+, silver plus is reacting to make silver, because that's the only way I can get a positive number there. It's going to be 0.03, so it's not going to be a very flash electrode, but let's go. So iron 2 is being oxidized to iron 3. Okay, so they're both in solution, so there's no state change there. So we just separate them with a comma. Iron 2 to iron 3, but hang on, that's still not conducts electricity, is it? I haven't got a metal in there, so we're going to need to add a platinum electrode as well. Platinum always goes on the outside of the cell representation. So platinum solid line, because I've got a state change, but then iron 2 and iron 3 are both aqueous, same state, same phase, so they can just be separated by a comma. Then we have our salt bridge, and now on the other side, silver plus aqueous ions are reducing to form silver metal. Silver metal, of course, can be used as an electrode. I can attach a wire straight to my piece of silver, so I don't need to have a platinum electrode there.